Hola, hola.
Bueno, bienvenidos los que apenas lleguen, los que estuvieron desde la mañana, pues bueno, gracias por continuar. Esta charla es parte del ciclo de conferencias magistrales de la UNAM, de la UAC, del CIMBESTAB. Y bueno, pues vamos a cerrar el día de hoy con la charla del doctor Michelangelo Mangano. Él es un físico teórico. Originalmente obtuvo su doctorado en la Escuela Normales Superiores en Italia y ahora trabaja en el CERN, en la división de teoría. Él se dedica a la cromodinámica cuántica, que es el área que estudia la física de los quarks. ¿Okay? Bueno, pues nos da gusto recibirlo y pues ya para no alargar esto, pues ya los dejo con el doctor Michelangelo.
Thank you very much for the introduction. Thank you for giving me the opportunity to visit you, to be here. It's the first time I come to Mexico, and I've always wanted to come. I'm happy I'm here finally, really enjoying completely my stay. I'm ashamed that I cannot speak Spanish. I can understand, so if you want to ask questions, you can do it in Spanish, and I believe I should be able to understand, but unfortunately, I would have to respond to that in English. I hope this is not a problem. So I will give you this brief overview of the physics that we do at the LHC at CERN. We do particle physics, so I will spend some time discussing what particle physics is, what are some of the tools, which way it helps us understand how the universe works, and then I will give you an idea of some of the things that we do at CERN. There will be more presentations in this series covering more closely the experiments at the LHC, covering the Higgs boson. On Wednesday, Professor P will talk about the Higgs boson in Spanish. So I will leave that for you. So I'll start from just giving you a very broad picture. The question of particle physics is one of the branches of physics, of course, and it's a branch of physics that deals with questions that humanity has been asking itself for a long time. Questions like, how does the universe work? Where does the universe come from? Where is it? Now, we ask these questions today in a more sophisticated way, of course, and we ask this question in terms of what are the active components of matter, so what is matter made of? What are the rules that control the interaction between the elementary components of matter, and what is the underlying basis behind all these rules? Now, it's not just the questions that we are asking that are very similar to the questions that the ancient philosophers were asking. It's also the approach that we follow resembles it very much. And the idea is to try to to describe electromagnetism, something completely different to describe chemistry, and something entirely different again to describe the way the galaxies and the stars move and behave. But that does not seem to be the case. We can really start from very, very few, very basic elements and describe the behavior of everything. Now, of course, what has happened in the course of history is that we are much more sophisticated today. We have, very complicated, we have a very advanced technology that allows us to make complicated experiments. We are also more sophisticated in terms of thinkers. In other words, when we say that we have proven that we understood a given process, a given phenomenon, we put to ourselves much stronger criteria of correctness, and I will give you just now in the next slide an example. The other thing that we have in common with the ancient philosophers is this identification of two main categories. One is the components of matter, and the other is the forces that control their behaviors. So we believe that out of these two categories, what matter is made of and how the components interact among themselves, we can describe everything else. We don't have to add other principles or other criteria. So let me give you an example. As you may remember from your courses of philosophy or history, once upon a time there were Greek philosophers who were suggesting that the fundamental components of the world were four. There was air, water, earth, and fire. And the forces were two. There was a force that was acting on air and fire, that was pushing them upwards, and a force that was pulling downwards the earth and the water. So that was good enough that, people could write articles about and become philosophers just for stating something which today we would consider very naive. And in fact, it's so naive that immediately you do find some inconsistency in this world, because, for example, if you take tree, the tree is like earth, and when it falls in the water, it doesn't go down, it just floats, it stays up. So that means that theory of the world is certainly incomplete. And then comes someone, Archimedes, who formulates, a new theory, an evolution of this idea, and he says, actually, all matter falls. It's not like there is something that goes up and something that goes down. Everything goes down. However, things go down with a strength, if you want, that is proportional, that is characteristic of their property. And today, we know that property is the weight. And then we say that a body immersed in water receives a push upwards that's equal to the weight of a displaced water. So in this way, we can understand how come that the tree floats, because it's lighter than the water. We also understand phenomena like the wind. The wind is due to the fact that hot air, of course, is lighter than cold air. So if we have some hot air, it goes up, it leaves a vacuum, that cold air has to come in, and that causes the wind. So all of a sudden, we have a theory that not only explains that apparent paradox of the previous theory, but also explains new phenomena and immediately becomes predictive. What is remarkable is that this theory is not more complicated than the one we started from, because we started from a theory that had four different components, two forces, and they were acting differently on these, and it wasn't quite clear why some should go up and the other should go down. Now we have a theory in which there is only one force, which is gravity, that pulls everything down, and it's a simpler theory, but it's a simpler theory that explains much more, that is more accurate. So the lesson here is that the improvement in our knowledge of how the universe works is not necessarily coming from making things more complicated. Very often it comes from making things much, much simpler, identifying symmetries, identifying principles which are broader, and that help us really get to the core of things. So for those of you who know a bit
the buzzwords of particle physics. One of the main themes is the grand unification, the unification of all forces, making sure that, gravitational, electric, and all the forces come from the same force. Well, we could see this example I gave you as maybe, a primordial example of unification of fundamental interactions. So that was thousands of years ago. Today, of course, we know much more. And the way we describe today nature is in terms of what we call the standard model. I assume you all know, you've all seen pictures like these. We'll start from the normal matter, everyday matter. We know that it's made of molecules. Molecules are made of atoms. In the atom, there is a nucleus surrounded by electrons. Inside the nucleus, there are neutrons and protons. And inside neutrons and protons, there is yet something else, which we call quarks. Beyond quarks, for all we know, there is nothing. So quarks indeed is the ultimate component of matter, is the elementary components out of which everything else is built. And the same is true of electrons. Electrons too, to the best of our knowledge, they don't have any substructure. We cannot take an electron, cut it in two, and find that there is something inside. Now, this is what we know today. It's not a dogma. It's not a theorem, it's an experimental fact. And physicists always test their own beliefs. And in fact, a large fraction of the experiments that we're doing at CERN with the LHC in these days aim precisely at understanding exploring whether indeed quarks and electrons are fundamental. And every time we collide our protons, we're really testing whether indeed there is not perhaps something inside the quarks. So these quarks are the fundamental entities out of which matter is built. There is a few of them. Those that contribute to forming the matter we know, so those that make the protons and the neutrons, are of two types, the up quark and the down quark. The up quark has charge 2/3 in unit of the proton charge. The down quark has charge minus 1/3. These two objects come together with the electron, which is the thing that goes around in the nucleus, and the electron has also a partner, which is called a neutrino, which is a particle with very, very, very faint interactions. And it's a particle that has charge equal to 0, so it's not, we cannot feel it using electromagnetism. It's a particle that appears in all of the processes of radioactive type. So the radioactive decays, for example, involve neutrinos. Now, this is what we call, this is what we call a family of elementary particles. And it turns out, experimentally again, that this family is replicated 3 times. There is 3 of them. There is a second family in which there is a particle that looks very much like an electron. There is a neutrino that looks very much like the neutrino of the electron. And then there is 2 quarks called the strange and the charm quark that behave very much like the up and the down quark that we find inside the proton and the neutron. The difference between these and those is that these are heavier than the ones in the fundamental family. And being heavier implies that when they are produced, they have a bigger mass and they tend to decay to objects which are lighter. This is a fact of nature. It's a fact of quantum mechanics that if you are heavy and there is a way in which you can transform yourself into something else, automatically you will go that way. And I will discuss this a bit more detail in the following. So that means that these particles are not stable. As soon as they are produced, they decay immediately to the lighter ones. So in order to see them, we have to artificially produce them, and that's why we need the particle accelerators like the ones we have at CERN. And finally, there is a third family, which is even heavier than the second one. For all we know, that's the end. So in terms of objects that look like the electron and the up and down quarks, there is only these 3 replicas that exist. And an open question, of course, I mean, these are those that we have discovered, of course, and the question is whether there is more. A question is also how come that there is 3? If the whole world is made just out of up quarks, down quarks, and electrons, because with those we can build atoms, we can build molecules, we have a chemistry and everything else. Why do we need 3 replicas of these? That's one of the big question marks in our research. So these are the elementary components, and then there are the interactions, so the forces that hold them together. Forces are responsible for what we call the bound states, which means literally holding things together. The gravitational force, for example, holds the Earth and the Sun together, the Earth in orbit around the Sun, and the electromagnetism holds the electron in orbit around the nucleus. But forces also, if we have particles with sufficient energy, they cannot bound them together, but they lead to a scattering, so a deflection. For example, the motion of an electron inside a metal, the electron is not bound, it moves around, but it moves around steered by the forces inside the metal. The propagation of light. If I send light going through a piece of glass or water, light, of course, will be deflected. As you know, there is a diffraction-refraction phenomena, and that is the result of electromagnetic interaction. So it's not the formation of a bound state. The photon does not get, bound in the glass. It just gets deflected. Or if you take a charged particle that moves through a magnetic field going around, of course, again. And then the other thing that forces or interactions are responsible for is something a bit more exotic, if you wish, and that's what we call transmutation. For example, atomic transitions, if we take the hydrogen atom with the electron in a very excited Rydberg state that then falls down to the ground state emitting radiation, that is again the result of the electromagnetic force. But what we see still was hydrogen before, it's hydrogen later, so it's just a transmutation, if you want, of the hydrogen atom. And likewise, nuclear decays and radioactivity are phenomena of transmutation type which are induced by the forces. So the fundamental forces are not many, there are very, very few. There are 4. There is electromagnetism, and the force is mediated by a particle called the photon, which is the quantum of light. The weak interactions, which are the source of all of the radioactive phenomena, are yet another independent force, and they're mediated by 3 objects. One is a neutral, so it's similar to the photon because it doesn't have electric charge, but it's very heavy. It has a mass of 91.188, 90. This 90 is in units, it's in GeV, which is one of the units that particle physicists use. 1 GeV is about the proton mass. So this Z boson is like 90 times, about 90 to 100 times heavier than a proton. And then there is a W boson, W plus and W minus. It has an electric charge with also a very heavy mass. Strong force, the force that binds quarks inside the proton and keeps protons and neutrons bound within the nucleus, is mediated by a particle called the gluon, which again has charge equal to 0 and has mass equal to 0. In addition to that, of course, we have the gravitational interaction, which we all know, and it acts on every particle that has any object that has energy. And finally, there is one more, which is the Higgs boson that's been discovered, as you probably heard, in 2012. The Higgs boson is not classified as, the fundamental components in terms of quarks and leptons, but also we don't classify it in terms of interactions. It mediates interactions, but it's interactions of a slightly different type relative to those which cause electromagnetism or weak decays, but it's still another object which belongs to this full classification of the fundamental particles and interactions. So now we had a bit few more things than they used to have, air, water, fire, and what was the other one? Earth, water, fire, and air. Okay, so we have 6 quarks, we have 3 leptons, we have the gauge bosons, but out of these things, we can really build and describe everything that we see around here. There are other forces in nature. There is the wind, there are van der Waals forces, there are many force concepts in the world, but each of them we can deconstruct down to some of these. The wind is the combined effect of electromagnetism and gravity. Electromagnetism, because it's electromagnetism what makes air becomes warm, because we have, say, photons, radiations from the sun, they hit the air, the molecules of air therefore get excited, they get hot, and they go up. They go up, why? Because there is gravity. And gravity is what makes the difference between hot air and cold air, and that's what gives rise to the wind. So the wind is not a fundamental force, it's the result of the electromagnetic forces and the gravitational forces. And everything else we see, you can always deconstruct down to this level. So the main conceptual results of this approach are the following. The simplicity, as I said, it boils down to few fundamental elements and few interactions. So it's a bit like the Lego game, the Lego sets, the Lego blocks, but we have few of them, and for those there are few rules in which we can assemble them. We can put them together like this, like that. We cannot put them together at 45 degrees because they won't fit. And out of these few rules and these few blocks, we can pretty much build objects of arbitrary complexity. Unity of the laws of interaction, the laws that, I listed them as electromagnetism, weak interactions, strong interactions, gravity. When we go and we look at the mathematics of these forces, of these interactions, it's exactly the same. So they have slightly different properties because they couple to different particles. So some particles are sensitive to electromagnetism, others are sensitive to strong interactions, but then the individual laws that describe these interactions are very, very similar, and we have a mathematical understanding of why that is the case. The unicity. When we talk about, you take 2 twins and they look identical. You buy an Apple computer, and you want exactly the same laptop that your friend has. So you go to the store and you give him the model. You tell him, I want exactly that one, which is, the MacBook, blah, 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 with those giga, and you have something that you believe is exactly the same as what your friend says. It will never be exactly the same, because you can imagine out of a gazillion molecules and atoms that this is built out, it's enough to go there and to scratch it a bit that I've already taken out some. So it will not be exactly the same. So in our daily life, there is nothing which is equal to anything else. In the world of elementary particles, it's exactly the opposite. A proton is a proton is a proton, as is written up there. In other words, it's not like, there is my proton and your proton. If I take a proton that comes from the Big Bang, a proton that was produced at the creation of the universe 14 billion years ago, and I take a proton that was produced at CERN in our laboratory artificially by just creating collisions. I take these 2 protons, I give them to you. There is no way you can tell which one has been around for 14 billion years and which one was just produced. If I give you a piece of bread that was made a month ago and a piece of bread that was made last night, of course you can tell the difference, right? With a particle, there is nothing like age, there is nothing like that. So, and that is, seems like a trivial statement or a trivial property. It's absolutely non-trivial because it has many consequences on the way particles actually behave. For example, as I was saying before, these heavier quarks, they decay. I produced like a charm quark, and it only lives for, in fact, a thousandth of a billionth of a second, so 10 to the minus 12 seconds, very, very short amount of time. A muon, the partner of the electron, lives for about a millionth of a second, 10 to the minus 6 seconds. Now, when particle decay, it doesn't decay because it's aged. It's not like when we die because we are old. And getting old means that all of the parts of our body are decaying, so we can tell the difference between a young boy and a very old man. The muon, you can never tell. If I take a muon, let's say that we actually could dilate the life of the muon from a millionth of a second to, say, 10 seconds, so that we have time to do measurements. During those 10 seconds, the properties of the muon will remain always exactly the same. There will be no sign of it aging, and at some point it just decides that it decays, okay? If it were changing in the course of those 10 seconds, then it wouldn't be true that a muon is a muon, because then it would be a muon with a given age. Particles don't have an age. They only have what defines them, namely the being a muon, the muonness, their charge, their spin, and that's it. Okay, so this is something quite remarkable. And the other thing is the uniqueness of the interactions. I mean, the interactions that were listed and the particles we listed there are not there to describe the physics on our world or in our laboratory. They really describe physical phenomena also in a distant galaxy. And in a distant galaxy in the past, so not just today. And of course, we can claim this because we can do measurements. We can do measurements in which we can, and it's almost as if we had an experiment built in a different galaxy. Because when we see the light that comes from the different galaxy, the light is the result of chemistry, of course, it's atoms, it's transitions. And when we measure the wavelength of the light coming from the galaxy, we can recognize precisely the same chemical processes that give rise to light on our Earth, in our laboratories. And we see absolutely no difference. And from that, we can infer the chemistry and therefore electromagnetism in different galaxies the same as we have. So the fundamental principles of particle physics are exactly the same as the fundamental principles of physics, of course. If you learn in school F equals to ma, that is valid also for elementary particles. You learn in school that conservation of energy, conservation of angular momentum, all of those things are valid also for particle physics. And in particular, Einstein's principle of special relativity that says that, for example, nothing moves faster than light, applies also to elementary particles. And in particular, quantum mechanics, which is laws of physics that apply to that apply at a fundamental level, apply to particle physics because, in fact, they originated from the observation of smaller and smaller systems like atoms, for example. So they are part of the world of particle physics. Now, special relativity plays in particular an important role because special relativity somehow is something that tells us that the rules of classical mechanics change slightly when we're dealing with objects that are moving very fast, with velocity close to the speed of light. Elementary particles are very light. And therefore, it's enough to just give them a little bit of a tiny force, and immediately they will accelerate to speeds very close to the speed of light. The speed of light is not relevant for us, for our cars, because the amount of energy it takes to send the car to close to the speed of light, it takes more than the amount of the uranium and the petrol that we have on Earth to actually put together enough energy to send a car to 0.999 the speed of light. So it's not our concern. But an electron, it takes nothing. The electron that goes around the nucleus, for example, in an atom, is already going at a speed which is very large. It's almost a hundredth of the speed of light. So it's not quite the speed of light, but it's close to it. Okay, that means 3,000 kilometers per second. So it's quite a lot. So that means that the effects of special relativity are very important in the description of elementary particles, and we have to take into account. And in particular, one of the things that, qualify special relativity is this idea that information cannot be transferred, cannot move faster than the speed of light. And this automatically implies somehow set some constraints on the way we describe the interactions, because if we have two particles separated by some distance, they cannot feel each other's presence instantaneously, because there is a distance between them. So any message between them, including the message of, I'm here, I am charged, if you are charged, you should move, that message requires the time. So the way we parameterize the interactions is by assuming that, let's take, for example, a couple of particles, which I put there as those two little blobs. At some point, one makes the other aware of its presence by sending a signal. So it sends a wave, it sends a signal. By sending this signal, at some point, this signal arrives to the other particle knows that I'm here, I'm charged positive, the other particle is charged positive, so two positively charged particles have to repel each other, and therefore it will recoil, or if it's negative, it will come towards me. So these simple-minded description we characterize in terms of these objects that we call Feynman diagrams. Here, the way to read this drawing is the following. Time is going in this direction, so we're looking at our particles, the blue and the yellow, as being here. They evolve. At some point, the blue particle emits a message. That's the idea of this radiation or this information being exchanged. At some point, this reaches the yellow particle, and the yellow particle will react and will recoil. Now, this is a drawing somehow to exemplify what happens. In reality, do we have another? Because this is, yeah, it's gone almost. I'm not sure that you can see it. Well, I still tried, but it's anyway. So in real world, there is a mathematics. I mean, each of these, no, it's gone forever. Each of those vertices up there corresponds to a mathematical expression that we manipulate in order to calculate the probability that something happens. So here, the picture somehow you see is characterized by having a description of the single particle emitting this signal, emitting this radiation, and then this radiation propagating between one particle and the other, and then there is the radiation, the signal, being captured by the other particle. Okay, so we break up these into two very simple elements, which is the localized interaction between the particle and that wave, that signal, that is what is responsible for the interaction. And we will see, but we also saw, we anticipated that's what, the photon or the gluon or the W boson will be. Now, this seems very simple, right? It seems like a very simple thing, but there is something very subtle underneath. And what's subtle is the following. I said I take a particle, and then I have a particle, and I describe this particle when it emits radiation, and then the particle remains. But if you look at it in detail, it seems a bit strange, because let's say I have a particle and I sit in the rest frame of this particle. So the total energy I have is the particle mass. A moment later, when the particle sends this information, sends this radiation, I still have a particle, and on top of it, I have the radiation. So the particle I have afterwards at least has as energy its own mass, so the energy cannot have decreased. And on top of it, I also create this radiation. So after, I have energy which unavoidably is bigger than the energy I had before. So by taking a particle and this radiating something, automatically I'm violating the principle of energy conservation. So there is something very weird in what I'm saying. Now, also this is a bit subtle, because you look at this and you could say, oh, but wait, but this is the way that light is created. I take the hydrogen atom, and the hydrogen atom in excited state emits radiation, and I find the hydrogen atom. Yes, but this is not the same, because the hydrogen atom that emits a photon, that emits radiation, is not the same that we have after the radiation. The one that emits is a hydrogen atom in which the electron is sitting on one of the excited orbitals. And it's because it's sitting in an excited orbital that falls towards its ground state that there is the space for energy being radiated. Now, the difference between these and the case of elementary particles is that, as I said before, a muon is a muon is a muon. So there is no something like the excited hydrogen state with the electron up there. If it's an elementary particle, there is no excited state of elementary particle, and this is why this is puzzling. And then, now in the next few minutes, we will do a small experiment that I will use to try to convince you of why, in fact, of how nature addresses this puzzle and solves it. Now, for this, I would have needed a blackboard. Without the blackboard, we can still do it, but it requires you to be a bit more attentive because I will be writing in air as opposed to on the board, and you have to remember what I've drawn, okay? So we say that we have a blackboard here, okay? Now, it's important for this experiment that everybody participates. So you all have to participate, to take responsibility, and you all have to do what I tell you. So I will now show you a slide in which a few points will appear. And you have to count those points. And you have to count them very quickly because they disappear. Okay, so you count them, and then you keep how many you counted in your head, and then I will ask you how many did you count, and you will tell me, and we make a graph, okay? So each of you has to answer. Even if you are not sure about how many you counted, still you have to give me a number, because if you don't, I shoot you. Okay, the fact that you're laughing means that you're following me. Good, I have to check because I want to make sure that you understand my English. So, count fast. How many? 6. Anybody counted different from 6? No. Okay. So we draw the result of a measurement. This is the board. I make a plot. Here is 6, and we make this peak. Okay? The peak contains the 80 people who are here in that peak. So that's the first part of the experiment. Now let's do the second part of the experiment. You ready? Okay. So, okay, 18. So 18, how many 18? Okay, so here is 18. Somebody counted 17? So we have 417, and I put 417 here. Somebody counted 16? No? How about 19? Okay, so there are 3 19, 20, and there is 120. 21 or more, 21 or more. So before we had the spike, and now we have something which is, 18, it was 17, and then 18, and then 19 and 20. Okay? And now we do the third experiment. Okay, so, and as I said, everybody has to say, because you were a detector, and the detector will switch it on and it tells me a number. It can be right, it can be wrong, but it has to give me a number, okay? So, say 15. Somebody counted 15? Okay, if you counted 15, it's like 6 of you, 6 count 15. Less than 15, somebody counted less than 15. There are a few below 15. 16. There is a few bit more than 15, there are 16, 17s. There you go, now we start counting. 18. 18, it's almost like 17. 19, a bunch, 20, A few, more than 20, still a few. Okay, we're done. So what have we learned? You see the picture, you see the board, right? The first experiment, we had a lot of time. We measured very, very well. The second experiment, we didn't measure very well. I mean, there was more, we don't quite know what the number was, right? In fact, at the end of the day, we don't quite know because people responded differently. You didn't have much time. In the third experiment, you had very, very little time. So you were not able to measure the number of points. So the bottom line is that if you don't have enough time to do a measurement, you don't know what the result of a measurement is. Okay? Now, you could say, well, but I can imagine, I can come in with a camera, and a camera with a computer, and the camera makes a picture of your dots. I have a program that immediately does pattern recognition, counts them, and in a millisecond would have counted the right number. Fine. And then instead of 5 seconds, I would have given you a millionth of a second. And then also the camera would have made a mistake. So, we can iterate, and we get down to really the earth of an important component of our nature, which is quantum mechanics. And it's the fact that if we don't have enough time, we cannot do a precise measurement. So when we say that energy conservation is violated when, my electron emits a photon, well, to state that energy is not conserved implies that I've been able to do a precise measurement of the energy before and after. And that requires that I had enough time. But if I only give it a short amount of time, then I don't know how much energy, whether energy was conserved or not, because I couldn't measure it very well. So what is important is that the moment my blue particle emits some radiation, something else happens, comes in, absorbs that radiation, and puts things back into place. Because if that happens over a short amount of time, delta t, then I can afford that delta E, that amount of energy, quote-unquote, violation, that the very first emission implied. Now, in the overall process, energy is conserved because the overall process you should be looking at like two particles coming in with the same speed. It's like two billiard balls. They come in with the same speed, they hit each other, and then they go out at a different angle. So they have deflected each other, but the total energy at the end or at the beginning is exactly the same, right? But each of them has in fact undergone a change because it was deflected. So, to the extent that we have a nearby particle that can contribute to the process, that diagram is fine and doesn't violate energy conservation. If there were no other particle, if the electron just emitted this photon and it has nothing to attach to, well, after time delta t equals to 1 divided by delta energy, how much energy the photon had, the photon has to go back to where it came from, and it goes back to the electron. So things are back in place. It's a bit like money. You can sign a check, you give me a check of, 1 million pesos. And it's fine, because whether you have it or not, it's irrelevant. Because I have to take the check and I have to go to the bank in order to cash it. So if by the time I go to the bank, I manage to put the money back into the bank, nobody will complain, because the money will be there. So depending on how much time there is, you can still live, out of... when you ask money to a bank, they give you money and they expect you to give it back at some point. So it's like a trade-off. It's like energy is being... When you get a loan from a bank, it's the bank that gives you money to allow you to do something. And once you've done it, you will put back that money because you are paying back, of course, the loan. And here nature works in a similar way. So it gives you a chance to bypass a bit this issue of energy conservation, which is a bit constraining. It's like saying, you have the money you have and you're stuck with that. It just gives you a chance to do something else. In this case, it gives you a chance to interact with something else, provided at the end of the day, you put energy back to where it was. And that is possible in all of these processes. So this is the way this picture of particles emitting radiation is consistent, and this is the basis of our constructing these building blocks of a standard model with which we build we describe all of the processes. So in the case of electrons, the electrons interact with the photon. Electron is the name we give to the electron-like particles. So the electron, the muon, the tau, we call them leptons. The leptons interact with the Z, which is neutral. You see the W has a charge. So when an electron emits a W minus, it cannot go back to an electron, because otherwise it would be a particle with charge -1 that goes to the W, charge -1, the electron, charge -1, so it would be charge -1 going to charge -2. And there is an important principle that says that the electric charge has to be conserved. And that means that when the electron emits the W, it has to go to a particle that has charge equal to 0, and that is why the neutrino exists. So the neutrino is the partner of the electron. So that also tells us that in the course of these interactions, it's not just that a particle emits radiation and remains itself. A particle emits radiation, emits a W, and can become a different particle. So we have a transmutation, we have a variation of, and this is the mechanism by which, for example, the heavy quarks decay. They decay by emitting a W and going to a different quark of a different type, which is lighter. The vertices for the quarks, in fact, are here. The quarks interact with the photons. They have a different charge. They interact with the W boson, and you see the quark becomes a quark prime, which means a quark of a different type. The up quark emits a W quark and becomes a down quark. If you do the counting of the charges, it turns out to be right. And the difference between the quarks and the leptons is that the quarks also interact with the gluons which are responsible for the binding of quarks inside the proton. So this is one example. You see that the three quarks bound together by gluons to form the proton and to form the neutron. Two up quarks and one down quark form the proton, two down quarks and one up quark form the neutron. And out of these simple rules, we can describe, for example, radioactivity. Radioactivity is the transition of a nucleus with charge Z to a nucleus with charge Z+1, an electron, and a neutrino. In the old days, when radioactivity was discovered, we thought it was just a nucleus going to a nucleus. Now we know that what is actually happening is that it's the neutron, one of the neutrons, that becomes a proton, transforms into... How come it's not? It's stuck. Oh my goodness. Sorry guys, what's going on? Yeah, bizarre. Anyway, so what is actually happening is that it's not just the proton, the neutron becomes a proton, but it's one of the quarks, one of the down quarks inside the proton that goes to an up quark, emits a W boson, and the W boson emits the electron, the neutrino. So we see we're using there separately the free particle object from the page of the leptons, where there was the electron, neutrino, and the W. That same W can also couple to the quarks, and these things are combined together to give rise to a diagram like this. So all of the phenomena of radioactivity, all of the phenomena that, for example, in the core of the sun are responsible for the energy generation of the sun, are related to processes of exactly this kind. It's transformations between neutrons and protons, and transforming protons interacting with each other into deuterium. Deuterium goes to helium, etc., etc. And the difference in charges creating neutrons being accounted for by the creation of electrons or positrons. Other ways in which we can combine the quarks are, for example, the pions. If we take an up quark and an anti-down quark, we put them together, we get the so-called positive pion. There is an antiparticle, which is the negative pion. We can do these games using strange quarks, using charm quarks, and we can build out of these the whole complexity of hundreds and hundreds of particles that we see in the experiments, that we see in nature when we probe nature. But there are not hundreds and hundreds of particles completely independent. They are all in their nature coming just from assembling in different ways a few very simple objects. So how much time do I have? Because I'm losing track of 5 minutes. Okay, so let me just finish because I still have a lot of stuff, but I don't want to rush. I will just spend the last 5 minutes to show you how we probe, for example, and we understand what is inside the proton, which is how we understood, for example, that there are quarks inside the proton. So let me take this picture. We have our proton, and let's say we have an electron, okay? An electron from the experiment, so it's not the electron going around the proton in the atom. And we shoot the electron with some energy towards the proton. And what happens is that as soon as they come close to each other, they feel that they're electrically charged, so they feel the electromagnetic field, and they bounce off each other. And they exchange a photon, and just they recoil. So doing this experiment has allowed us to notice that the proton does not react as if it were an elementary particle. Because if we start increasing a bit the energy of the electron starts going a bit inside the proton, and then it sees that, there is some structure. And, the details of how the electron recoils already in the early 60s had suggested, early 60s of the last century, so we're talking about 50 years ago, has suggested that indeed the proton has a structure. There has to be something inside the proton. Now, if we go to electrons now with a higher energy, so we increase even more the energy, because we want to go even deeper inside the proton, what happens is the following. The photon comes close, exchange a photon, but now there was more energy, and what happens is that we put the proton in oscillation in excited state, and it has so much energy that at the end, as a result of oscillation, it just splits into two, and it creates another particle. So we have a proton, we excite the proton, this proton starts oscillating, and then out of this energy emanates a new particle, which is a pion. Okay, so this is already something completely different with respect to what we had before. And the study of this process is in fact what started leading to the understanding of the nature of the forces that hold quarks together. Now, what has happened in this? What has happened is explained in the next slide, which illustrates one of the key and most somehow fascinating properties of quarks, which is the confinement. The fact that there is no way we can actually isolate a single quark. If we take an atom, which is made of protons, nucleon, and the electron, we can separate the electron from the atom, and we can hold the electron almost in our hands. The question is, if the proton is made of quarks, can we take it apart and hold the quark in our hands? And the answer is no. And the reason is this one. So let's take our proton. The proton is up there. You see two up quark and a down quark. And as you see, I'm stretching the up quark, trying to pull it away from the other two quarks. And I do this by, shooting, giving the big kick with the electron I had in the previous slide. So the electron comes in and gives a big kick to one of these quarks. And then what happens, as I try to separate this up quark from the rest of the proton, is that there is a huge force between them. And this huge force, it's a force, in fact, which is constant, so the energy, the potential energy, grows linearly with distance. And as soon as I've put enough energy into the system trying to separate these two, I have enough energy, using Einstein equation, E equals to mc squared, to produce a quark-antiquark pair. So if I put energy in the system, instead of taking away the quark, what I do is that that energy goes into creating a quark-antiquark pair, and at that point, the antiquark pairs up with a quark. The up quark that I created from this pair pairs up with the rest, and I end up having, you see, a proton, which is what I started from, plus this U and U bar quark, which is the pion. So this is what happened in the previous slide. I tried to put energy into the system, and instead of taking out a quark, I just I created another quark-antiquark pair, and I broke it up. It's a bit like taking a spring. If we take, a very strong spring, and we pull it, at some point it breaks. And by breaking it, at that point, the two halves of the springs, they are free, and they go away. Okay, but I've not been able to really separate one end of a spring. I'm always left with a full chunk of it. So this is the confinement, and this is why we talk about quarks, but we've actually never seen them directly. We've not been able to separate, to pull them out, but this notwithstanding, we have a theory of how quarks interact. We understand very well the proton interactions. We use them to create a very complicated final state by colliding protons together, and we analyze them using complicated detectors. This is an example of the result of two protons colliding and giving rise to two streams of quarks and gluons. And to do that, we need high energy, because it's high energy what allows us to go and take these snapshots with a very, very fine time resolution, because again, of the uncertainty principle that I was describing before, and to get this high energy, we need to build these huge accelerators like the LHC. And I will spend just 1 minute now to show this last slide. This is the Geneva area, that's the Lake of Geneva. To give you a sense of the dimensions here, here is the airport. This is so you see this is few kilometers, right? And underground, 200 meters, between 100 and 200 meters underground, there is this big ring. It's 27 kilometers, the circumference. And this is where protons are accelerated. They start from a smaller injector where the proton is created from the source. We take a proton from a tank of hydrogen. We just kick away the electron, and we have a proton. It gets accelerated. It's a bit like the car. You cannot start in the 6th gear. When you start with a car, you have to go through 1st gear, 2nd gear, 3rd gear, 4th gear, and here it's the same. So the 1st gear is this linear accelerator, and then there is a small circular accelerator, the proton going to the bigger one, and then into the bigger one, and finally into the LHC, where they're brought to collision. There are protons going one way, protons going the other way, and they collide and interact in few specific points where there are the experiments. So I'm afraid my time is over. Still, I hope I managed to give you an overview of at least some of the fundamental principles. From here on, if you're interested in the technology, in the experiments, etc., I believe that the lecture by Professor Sfikas on March 16 will cover that. And if you're interested about the story of the Higgs boson, March 15 on Wednesday, there is the lecture by Professor Pick who will cover that. So I'm done, and if there are questions, I'll be happy to reply.
¿Cree que pudiera haber alguna manera de utilizar la energía que mantiene a los quarks unidos? O sea, ¿do I ask you in English or in Spanish?
It's okay, I understand.
Dijo que los quarks están unidos con una energía tal que al momento de separarlos les es más sencillo crear otro quark que separarse entre sí. ¿Cree que de alguna manera en un futuro tal vez no muy lejano pudiéramos utilizar esa energía?
No.
No, I mean, it's a fantastic question because indeed, you know, things like nuclear power comes by using the energy that holds protons and neutrons inside the nucleus, and therefore it's legitimate to ask whether we can use the energy that binds the quarks inside. There is a huge difference. First of all, if you want to take out a quark to free that energy, you have to put energy in. That's the problem. I told you, you know, at some point there is enough energy that we can create a quark-antiquark pair, and then we split the two. But that energy, it's me who put it in. Okay? We get energy out of nuclear decays because those nuclei are already in an excited state. They're in an excited state that will allow them to decay. But they got into that excited state because they got there, you know, during the past history of the cosmos. They were created typically during the explosion of a supernova star, the last phase of a very, very massive star. There are these, there is a huge collapse onto the core. There are huge energies coming from the implosion of the star towards its nucleus, and those energies get converted into the creation of these very, very massive nuclei, like, you know, the various versions of uranium, etc. And those are there just waiting to decay to their fundamental energy, the ground state. And that's the energy we are using. So we get it for free. It's a bit like petrol. Petrol, you know, you pull it out and you use it in your car. But it's because it's already there. It's the history of the universe that created that energy. When we take a proton, the proton is already in its ground state, and we cannot pull out any more energy from it. Okay? But it was a very good question.
Bueno, se nos dijo en una conferencia pasada que un neutrón, la subida promedio es de 15 minutos libre. Entonces, ¿qué es lo que hace que el neutrón sea estable cuando está en el núcleo?
So let me see if I understood. You say you learned from the conference that the neutron as itself has a lifetime of about 15 minutes, and you are wondering why the neutron remains stable inside the nucleus. Okay, so that's the question. Again, an excellent question. It's true, the neutron has a lifetime by itself of about 1,000 seconds, which I think is consistent with the 15 minutes. When the neutron decays, when it's free, it decays to a proton, an electron, and a neutrino. And it decays in this way because the mass of a neutron is bigger than the sum of the masses of the proton and the electron and the neutrino, otherwise it couldn't decay. When the neutron is inside the nucleus, if the neutron were to decay, it would go into a proton. And the proton has a smaller mass, but if it's a big nucleus where there are many other protons, it feels the force of the other protons. And many protons don't like to stay together because protons, they all have positive charge, and particles with the same charge, they repel each other. That means, in terms of potential energy, that there is when the neutron becomes a proton, all of a sudden there is an additional contribution to the energy, which is the potential energy of a proton interacting with the electromagnetic field of a nucleus. And that energy can be larger than the mass difference between the neutron and the proton. And therefore, it's not convenient for the neutron to decay. And therefore, it prefers not to decay and it stays stable. So it depends from the nucleus. There are nuclei, for example, the one I used in my example, you saw I said it's the neutron that decays to the proton, right? But typically it would happen only for few and not for all of the neutrons, because once you start, otherwise you would have a nucleus which is all made out of protons, and that would just explode, right? Because there would be so much electromagnetic force that it would just take it apart.
Yes, so, oops. Yes, you mentioned that information cannot travel faster than the speed of light. And well, as we know, because due to Hubble observations, the universe is expanding. does this mean that right now we cannot achieve, a faster than light space travel or anything like that? But does this mean that we are forever kind of blinded from getting to know a part of our universe, because the universe is expanding, and at the end we cannot go farther away than what the space is already expanding to? I don't know if I explained it.
Yes, absolutely. There are parts of our universe from which we are, as we say, causally disconnected. So there is no way we can interfere and we can learn from each other. So yes, absolutely. Maybe there is your girlfriend in that universe and you will never get to see her. I know it's frustrating, but we have enough good girls in Mexico, but you don't need to go very far for that.
When I read about particle accelerators, I often read about synchrotron light, no? Lose the synchrotron. So could you tell us what it is and why is it useful?
So synchrotron radiation is light, is photons. It doesn't necessarily have to be light in the sense of visible. It can be a different wavelength. And it's the result of charged particles being accelerated. When a charged particle is accelerated, it emits radiation. And it is a bit connected with what we said before. Before, when I was describing the impact of quantum mechanics on the interaction, I said we had the electron emits a photon, and then this photon, if there is something around, the photon couples to that, provided we have a short time. Otherwise, the photon has to come back and reconnect with the electron, because otherwise it's a virtual state, it cannot live forever. But if after this photon has been emitted, I suddenly change the trajectory of my electron, because maybe there is an electromagnetic field, an electric field, and I change the trajectory, only the electron gets deflected, because the photon is neutral, so the photon would not feel the presence of the electric field, and at that point the photon just goes forward. So that means that whenever I take an electron or a charged particle, and I make it turn, it will radiate. It will lose radiation. And that radiation is what we call synchrotron radiation. The name synchrotron comes because the accelerators that make electrons go on a circular path, they are called historically synchrotrons. So it's radiation that comes from electrons inside the synchrotron. And that is an important consideration, because if the electron is losing energy, we have to put that energy back if we want it to keep continuing going on. So for us, who are only interested in getting the electrons of energy as large as possible, synchrotron radiation is a pain in the neck, because we have to, keep putting energy into the system. On the other hand, those beams of synchrotron radiation, those beams of light, can be useful to study the properties of matter, for example, of in solid-state physics, and or even in biology. If you want to look at some molecules or you want to look at some reactions, you actually use these beams of light, which typically have a very, very, very short wavelength, as supermicroscopes. And then, in some places, they build accelerators not to study particle physics the way we do, but just to generate this synchrotron light, and use that in order to go and look inside the matter.
Sorry, perdón. What is the supersymmetry theory about?
Tough question. What is supersymmetry? How many of you have heard of supersymmetry before? Oh gosh, everybody. You know more than I do. So supersymmetry is, in the space-time, which is what surrounds us, there are symmetries related to, for example, translations. If I do an experiment here, or I do an experiment here, I will get exactly the same. The laws of physics are exactly the same. If I rotate my frame, I can say that that is forward, this is upward, and this is leftward. I can turn around 45 degrees, and I still say that that is forward. The experiments are irrelevant. It doesn't matter which way I turn. The laws of physics, the Coulomb's law remains the same. An electron and a positron attract each other, whether I do the experiment here, looking in that direction, or if I turn them around, they still interact in exactly the same way. This is a symmetry. The fact that the result of measurements is the same is what we call is a symmetry. And the symmetry that I just described is the symmetry of space-time. It's called the Lorentz symmetry. It turns out that it's possible to identify another set of symmetries in our space-time that enter when we allow for the existence of particles that have a spin. So it's a typically quantum mechanical property of a space-time. And if this symmetry were true, were realized in nature, automatically that would imply that for each particle that we know, there should be another particle which is related to it by this symmetry. And it's a particle with a different spin. So the particles like the quarks and the leptons, which we know, they spin 1/2, so they rotate among themselves, they would have a partner which has a spin 0. The photon would have a partner. So our universe of elementary particles, if supersymmetry were true, would be doubled. There would be another set of particles that are required by that symmetry. So since we don't see those particles, it means the supersymmetry cannot be true. But it could be that it's not true because it's broken. In other words, the symmetry is there, but there is something that makes it not active, in a sense. And the result of this is that all of these particles, yes, they exist, but they are very, very heavy. And that's why we haven't seen them. So the search for supersymmetry is a search for particles which are the partners of the particles we know, of mass possibly larger, and that if they were discovered, they would tell us that space-time has this additional symmetry. And that would be very important because that symmetry, for example, is the basis for superstrings. It's a basic for the understanding of the correlation between gravity and quantum mechanics, so it would be a monumental result. You should ask him, I'm not...
Okay.
She's curious about something. How is the LHC clean?
It's not clean.
The LHC is something so complicated that you cannot possibly have an idea. I mean, the LHC is much more complicated than, going to the moon or anything else. It's beyond belief how complicated the thing is. And cleaning it, as part of that, can also be very, very complicated. Because there are, it's not just the cleaning like washing the floor, but all of the components indeed need being refurbished. So it's not cleaning in the sense of making it shine, but keeping it functionally operative. And maintenance is really a very complicated thing. So, yeah.
Hola, buen día, gracias por la conferencia, estuvo muy interesante. Y bueno, quiero preguntarle qué me puede decir respecto, esta es la física de los átomos que constituyen a la materia que todos conocemos, pero ¿qué respecto a la materia oscura?
The dark matter, we know, has to be a particle. So in principle, it is one of the fundamental objects that I described. But we know that it cannot be any of those on our list. So indeed, dark matter is something that we have to take us beyond what we call the standard model. But and we're looking for it. In principle, it can be created in the LHC, So we could be able to discover dark matter by directly and understand what it is from the LHC. We will need to add some more pieces to that picture. I don't expect that it will be, I mean, it will be a revolution because dark matter is something that, you know, populates the cosmos, so intellectually it is, but it's not like all of a sudden we need to change quantum mechanics or we need to change electromagnetism, or so it will just be another particle that we will add to our picture, and the LHC is looking for it.
Thank you for a nice conference, Dr. Mangano. One student physically intermediate report of evidence. Thank you. Chicos, la verdad, muchísimas gracias. Ya vieron que vamos subiéndole bastante el tonito a la calidad de este tipo de conferencias, así mismo vamos esperando ir mejorando nuestra carrera cada vez, esperamos, tenemos más expectativas porque los ingenieros físicos de la Universidad Autónoma de Querétaro sean los mejores a nivel de México, a nivel de América Latina y por qué no decirlo, del planeta Tierra. Bueno, pues muchísimas gracias, los esperamos con mucho gusto para el día de mañana. También tenemos las otras participaciones de los doctores que también están participando en la Escuela de Física y Altas Energías, en estas conferencias simultáneas. Vamos a tener al doctor Auditorio, va a hablar del bosón de Higgs. Vamos a tener a Paris Pica, viene de la Universidad de Atenas, y nos va a estar hablando sobre estudiando la naturaleza con billones de electronvolts, como comentó el doctor Michelangelo. Y obviamente Federico Sánchez, Alejandra Ayala y Miriam Mondragón, que también nos estarán recreando mucho por este maravilloso mundo de la física y de la física a pequeña escala, que nos va a llevar a grandes cosas en la macroescala, ¿no? Entonces por aquí los estaremos esperando con el mayor de los gustos. Un aplauso para todos, como en la mañana. Estamos muy contentos. Recuerden que los chicos que necesitan la justificación, estoy terminando de llenar la lista para en la tardecita, por ahí unas 2 horas ya le van a estar llegando a su correo electrónico. ¿Sí? Si se quieren tomar una foto con el doctor Michelangelo, aprovechenlo.
La justificación que va a mandar en los correos electrónicos, ¿qué es?
¿Te quieres apuntar?
Sí.
Las clases.
Sin parpadear, a la cuenta de 3, 1, 2, 3.